Hello everyone, my name is Chung, or you can call me Edgar. Today, I'm here to present about Provably-Safe neural network training using hybrid Zonotope Reachability analysis. Traditionally, when we think about neural networks, we put in a point of data and it outputs some point of data. A different way to think about neural networks is in terms of sets, meaning that if the input is anywhere within a compact set, the output point should also lie within some compact set. In this talk, I'm going to go through three things. 1. How we can describe compact sets. 2. How we can compute the output sets in this set representation, which is known as the neural network reachability problem. And 3. If we have some unsafe sets in the output, can we train the neural network in a way such that the output set would avoid the unsafe set? This is known as the neural network repair problem, and is the main contribution of this work. At the end, I'm going to show some practical applications of our method and hopefully convince you why this problem formulation is useful. So how do existing methods repair neural networks? One way to do it is by training with counterexamples, where you identify an output point that is unsafe and derive a cost function to penalize the collision. The problem with this is a whack-a-mole problem might show up, where making some points safe may make other points unsafe. The other way to do this is to formulate the penalizing cost functions in terms of the set under violation, which is what we did in our previous work. The problem with our previous work is that 1. The computation speed scales exponentially with the size of the neural network, and 2. It can only handle convex unsafe sets. In this work, I'm proposing a set-based method that scales linearly with the size of the neural network and can also handle non-convex unsafe sets. To start, let's talk about how to represent non-convex compact sets. To do this, we leverage a set representation called hybrid Zonotope. This is the formula for hybrid Zonotope, which looks intimidating, but let's break it down. The infinity norm constraints describe a unit hypercube in some hidden dimensions. The equality constraints describe a hyperplane in the hidden dimension. So with the infinity norm constraints, we have some slice of the hypercube. The affine operations on the left transform the slice in an affine way where the generator matrix GC can project, rotate, stretch, or skew the slice. And the center vector C translates the slice in the output dimension. So what we have described up to this point is called a constrained zonotope, which can describe any polytopes, meaning compact shapes with finite number of faces. Now in hybrid zonotope, we have these binary coefficients that enables us to express multiple constrained zonotope at once. Hybrid zonotope is a very powerful representation because it can represent a union of polytopes which are convex and compact sets. We can describe many non-convex constraints with hybrid zonotopes, and hybrid zonotopes also supports a lot of set operations. Particularly, it has been shown that hybrid zonotopes can exactly describe the output set of a ReLU neural network, with the complexity of the representation scaling only linearly with the number of neurons. Now, remember, our problem is that there's some unsafe set from which we want to drive the output set out of. And to train a neural network to do this, we need to quantify some signal to tell us how bad the output is in collision, or not in collision. Now, although there are existing optimization programs that can tell us whether the output set has collided with the unsafe set or not, these signals are binary, which are not helpful for learning at all. So here's an idea. What if we formulate collision as how much do I need to shrink the input before the output no longer collides? Or if the output is not colliding, can I get some number to tell me how much do I need to enlarge before the output collides with the unsafe sets? If we can do this and the quantification is differentiable, we should be able to train the neural network to drive the output set out of collision. So how do I do this? Well, let's look back at the formulation for hybrid Zonotope. In our method, instead of using hybrid Zonotopes directly, we propose a new concept called scaled hybrid zonotopes. Basically, instead of having an upper bound of 1 in the infinity norm, we parameterize it with a scaling factor r. This means if r is less than 1, we're shrinking the hypercube and therefore shrinking the hybrid zonotope set. If r is larger than 1, we're enlarging the hypercube and therefore enlarging the hybrid zonotope set. Essentially, scaled hybrid zonotope, as the name suggests, enables us to scale the size of a non-convex set with a parameter. It also turns out that the math to pass a scaled hybrid zonotope through a neural network stays exactly the same as that to pass a hybrid zonotope, except with the infinity norm upper bound changed from 1 to r. This enables us to tell how much the output set will shrink or grow from shrinking or growing the input set. Now let's look back at the problem we want to solve. We want some way to quantify how much to shrink or grow to quantify the severity of the collision between the output set and the unsafe set. And because we can control the size of the output set by adjusting R, we are asking the question, what is the minimum R such that the output set still touches the unsafe set? So you can imagine if the output set is not in collision, then this minimum R will be larger. And if the output set starts off colliding, then the minimum R will be smaller. So this R is a way to quantify how badly the output set is colliding with the unsafe set, which we can ask our neural network to optimize it. It turns out we can use a mixed integer linear program, or MILP, to calculate this minimum R. And actually, by solving this MILP and looking at the optimal R, we can immediately tell if the output set is colliding with the unsafe set or not. The problem is that MILPs are hard to solve, and they are not directly differentiable, which is what the neural network would need for training. To overcome this, we leverage a technique of obtaining the gradient of the MILP by relaxing it into a linear program, or LP, which we can differentiate and is much easier to solve. And now by following the gradient, we can drive the output set out of collision. The drawback is that because the optimal solution of the LP is an upper bound of the solution of the MILP, we lose the ability to track whether the output set is colliding with the unsafe set. In practice, while we still use the relaxed LP in training, we run the MILP every few iterations to see if safety has been achieved. The main contribution of our method is that we believe we're the first to drive a neural network out of non-convex constraints with sets. And even if the constraints are convex, because the hybrid zonotope scales linearly instead of exponentially with the size of the neural network, we significantly outperform our previous work, which cannot even handle any neural networks beyond 30 neurons. Okay, so this technique is cool and all, but how is it actually useful? Now let's look at how we can apply them to problems in decision and control. Consider a discrete time dynamical system that takes in the current state and control and outputs the next state. If the current state is anywhere within this screen set, then it reasons that the next state should also be some set of states. One way to certify safety of the system is called forward-invariance, which means that the output set must stay within the input set. So can we design some neural network control policy such that the control would drive the output set within the input set? To formulate this into a problem we can solve with our method, we simply need to define the unsafe set as the complement of the input set, and use our loss function to drive the output set out of the unsafe set. Here, we train a neural network controller for a double integrator system. You can see that by following the gradient that we came up with, the system gradually becomes forward invariant. Now, the previous example was showing safety for one time step, but it's usually more useful to certify safety over an entire trajectory. Consider some parameterized dynamics that are learned from neural network that takes in the initial state, time, and trajectory parameter, and outputs the state at the corresponding time. Trajectory parameter can be things like PID gains or target velocity depending on, how the trajectories are parameterized. Again, if the initial state is anywhere within some set, then it reasons that the future state is also bounded within some sets. Now, because we want to certify safety for some length of time from 0 to some final time tf, we can also consider the time as a set. This would draw out the trajectories in the future state. A different way to understand this is to treat time as a separate axis, so we can see how the trajectories evolve as time increases. Now let's say we have some obstacles with which we want to avoid. Well, the obstacles should not be collided at all times, so the unsafe set would be this column here from 0 to tf. And now let's say I want my system to reach some goal by tf. In other words, at tf, the trajectory should not be anywhere but the goal. So we can draw the unsafe set as a sheet of the goal's complement at tf. Now, it is not correct for us to alter the dynamics in any way, so what we're trying to train is actually a neural network policy that determines what parameter and therefore what trajectory I should be tracking. And we can now use our method to drive the trajectory out of the obstacle and into the goal. In robotics, an example of a system where the trajectories are so complicated that they need to be learned with neural networks is drifting cars. Here, we can see that an initial policy is originally colliding with the obstacles. The trajectory parameter in this case is the speed and angle to start drifting. We want to use our method to determine the trajectory parameters that will make us drift into the goal while avoiding obstacle cars. This is exactly what happens when we apply our method. So our method has three main limitations. 1. We cannot a priori verify whether a neural network is repairable. For example, it may be the case that there exists no policy that can make the car drift safely in between two cars. We won't know before attempting to solve the problem. Second, like all neural network training methods, the performance of the method is sensitive to hyperparameter choice, like network size, initialization, or learning rate. And third, because we're working with hybrid zonotope, the method is limited to ReLU neural networks. The one-sentence summary of this talk is that we designed a differentiable loss function that can train ReLU neural networks to obey non-convex constraint. Thank you for listening to my talk.